Hello and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And today we will be discussing the latest release of GHEtool Cloud, and namely the introduction of inlet and outlet temperatures in GHEtool Cloud. Now, before we start, let us recap, because thermal bore field design is always about temperature profiles. And these are typically the profiles you work with. They can either have a monthly resolution or an hourly resolution. On the slide you see one with a monthly resolution, where we have temperatures during peak cooling and peak heating, and we want them to stay within certain limits that are both driven by sustainability requirements, durability, as well as legal reasons. Now, typically the fluid temperatures you see on these graphs, and that's the way it has also been historically in GHEtool, are the average fluid temperatures, which mean it's the difference between the inlet and the outlet temperature of your bore field. So in case you see here, we're going down to 0 degrees during our peak heating after 25 years. This is the average fluid temperature inside of a borehole. Now, to understand this a little bit further, let us talk a little bit about what goes on in the background. Because the way these profiles are simulated in GHEtool is that first we calculate the borehole wall temperature. As we discussed when we were talking about the long and the short-term effects, both videos are linked in the description, we said that, well, everything starts from the temperature of the ground. And because our bore field is a ground heat exchanger, so we need to know the temperature from the ground, which changes month to month, hour to hour, year to year, since we are injecting and extracting energy in and from the ground. So the first thing we do is use these G functions to calculate how the borehole wall temperature evolves over time. And that's basically the start of all our fluid calculations. The second thing we need to do is to calculate the effective borehole thermal resistance. Now, why do we need this? This is effective borehole thermal resistance. It tells us something about the heat transfer inside our borehole, how easy it is for the fluid to transfer its heat to the pipe, to the grout, to the borehole wall. And this effective borehole resistance, it's, as we discussed, a function of the flow rate. And in GHEtool you can work with variable flow rate. It's a function of the fluid properties, viscosity and so forth, which also vary over time. So we calculate the effective borehole resistance during heating and cooling, and if you do an hourly simulation, at every hour. And since we now know the borehole wall temperature and we know this effective borehole thermal resistance, we can calculate the average fluid temperature using this resistance. Because if you recall, the borehole resistance, it's basically defined as the temperature difference between the borehole wall, the average borehole wall across its length, the average fluid temperature inside the borehole, and that's and the power we extract or inject at a certain moment. And since we know the power, we know the borehole wall temperature, we know the borehole resistance, we know also the average fluid temperature. And that's where the story ended for GHEtool and Earth Energy Designer and other design software in the past. Now, today we released an extra option, a fourth option. It's that namely we can also now calculate the inlet and outlet temperatures directly. And the way we do that is we know from step 3 the average fluid temperature and the average across the entire borehole. But we also know the flow rate, which again can be constant or variable. And we have this very famous formula we already covered in the past that says, well, if we have a certain power being extracted from the bore field, for example, that power is equal to the mass flow rate through this bore field multiplied by the specific heat capacity of a fluid, which we know for a certain temperature, multiplied by the temperature difference between the inlet and the outlet. So for a constant flow rate, if we go from, let's say, a delta T of 3 to a delta T of 4, we increase the power we extract by 33%. That's just a very simple and very elegant formula in the world of heat transfer. But since we know, again, the power, we know the flow rate, we know the specific heat capacity, and we have also this delta T, and since we know the temperature difference between the inlet and the outlet, and we know the average fluid temperature, we hence also know the inlet and the outlet fluid temperatures. So let us now discuss why we need 3 different temperatures, or at least what you can do with it, what you can learn from it. Now first, the average fluid temperature, the average between the inlet and the outlet, is basically what you've been working with before. It's used by the effective borehole thermal resistance, and it's the straight relationship between the borehole wall temperature on the one hand and the average fluid temperature. And what is good about this temperature is that we do not care about flow rate directly. And we do care about flow rate to get up with our Reynolds number and our turbulence and so forth. But we do not need it for the temperature calculation itself. And we just use the average, so we do not care if we are, for example, working at regime 0 degrees in the borehole, 3 degrees out, or let's say 5 degrees in, minus 2 degrees in, 5 degrees out. It's all the same average fluid temperature. So it makes it really straightforward to work with. The downside, however, is that if we say, well, we have an average fluid temperature of 0 degrees, let's say, well, inlet temperatures will be lower. And if we want to have certain strict thresholds on fluid temperatures anywhere in our bore field, we need to look at the inlet temperature instead. So the inlet temperature is the temperature going into our bore field. And this is basically the worst case situation you can have, because it's always the coldest when we're extracting heat and the warmest when we're injecting heat. And the reason for that is that we have our heat pump, and our heat pump is heating our building. The heat pump gets temperature out of the ground, it extracts the energy from the fluid, and this colder temperature with fewer energy, this colder fluid gets re-injected in the ground. And it's this point after the heat pump, right before we enter the borehole, that the temperature is the coldest. When we're injecting heat, and our heat pump is, for example, being used to dump the heat from the building into the fluid, to extract the cold, let's say, the temperature going into the bore field is actually the warmest of our entire primary circuit. So the inlet temperature are the absolute minimum and maximum temperature, and if we want to put limits in place, like there is some regulation in specific countries, especially on this inlet temperature, we know that if we say between 0 and 25, there is no fluid anywhere inside our bore field that will be below 0 or above 25. So it's the best or the safest way to design, because you directly control the temperature. Now, on the other side of the spectrum, we have the outlet temperature. That's the temperature coming out of the bore field. That's basically the most optimistic temperature. It's always the warmest during extraction and the coldest during injection, because, yeah, we said before, we have our heat pump, and during heating it extracts the heat from our fluid and it injects it really cold, for example at 0 degrees. It travels through our heat exchanger and through our bore field, and it comes back at 3 degrees. It comes always back warmer. And the same when we're cooling, when we're injecting heat, it always comes back a little bit cooler. So our outlet temperatures are actually, yeah, the most optimistic one, the warmest during extraction and the coldest during injection. These temperatures are the temperatures going into the heat pump, and they are important because our heat pump, at 5 kilowatt, 10 kilowatts, 100 kilowatts, they have a certain rated power. And this rated power is only, or the heat pump can only deliver this rated power at certain temperature inlets of the heat pump. So for example, typically residential heat pumps are designed, or they have a rated power at B0, W, 25, 55, something. So we need to make sure that if we want our heat pump to function, that our inlet temperature of the heat pump, which is the outlet temperature of the bore field, it's a little bit confusing sometimes. So the inlet of our heat pump, the temperature coming out of our bore field, stays above this level in order to make sure that the heat pump has the capacity we need to heat our building. But again, if you design for the inlet temperature, same threshold, since the inlet temperature is always a little bit worse than the outlet temperature, it's colder or warmer depending on extraction or injection, you're always safe on that side as well. So this was a little bit theoretical. Let's jump into GHEtool Cloud and show you real quick how you can switch between average inlet and outlet temperature, and how that influences your temperature profiles as well as your required total borehole length. So here we are in GHEtool Cloud. I created a new project, and as you can see, what has changed in this latest update is that the simulation settings, they now have a button to select your type of temperature. So by default, and historically, it's been the average fluid temperature between the inlet and the outlet, but you can now also select the inlet and the outlet temperature. Now, what I want to show you in this example real quick, it's a bore field with 4 boreholes. There is a W heat exchanger with a constant temperature difference for the flow rate calculation. So we will work with different flow rates in heating and cooling as well from month to month. And this is our thermal demand. So it's 15 kilowatts of heating, 6 kilowatts of cooling, and a certain amount of kilowatt hours per year in heating and cooling. So let us go ahead, go to the results. And here you see the temperature profile you're again familiar with. But now for clearness, we added average besides the label. So we know next to the label, so you know which temperature it is we're talking about. So here you can see we go down to 0.46 degrees Celsius, minimum average fluid temperature during the peak, which is above 0 degrees. Now let us go ahead and do the same calculation, but now for the inlet temperature. And I will also already duplicate it again for the outlet temperature, because as you know, you can run multiple simulations simultaneously in GHEtool. So let's run them and see how the design or how the temperature profile changes when switching from the average to the inlet or the outlet temperature. So for the inlets, as said, this is the worst case situation, and you see we're now going down to negative temperatures. And we go down to minus 1.04 degrees going into the bore field, which is indeed significantly colder than our 0.46 degrees Celsius we had with our average temperature. Same with the maximum temperature, it's now also higher, 17.6 when compared to 16.13. The outlet, on the other hand, is more optimistic. Here we're almost at 2 degrees, and you can see, yeah, we still go down, but there is a difference. And what is interesting is that if you take the inlet and the outlet, and we see here it's 1.96 degrees Celsius, here it was minus 1.04. That's exactly a difference of 3 degrees Celsius, and the same difference we also set when we say, well, let's work with temperature dependent flow rate of 3 degrees. That 3 degrees we also see back here. So that's a little bit how this works. So again, the inlet temperature, it gives you the worst case situation. If you want that every temperature inside your bore field is above a certain or below a certain limit, you need the inlet temperature to work with. Now this has also some effect on the required borehole depth. So let us go ahead and simulate it as well for the inlet, for the average temperature. And let's do the same for the inlet temperature as well as the outlet temperature. So if you look at the result with the average temperature, we're at 0 degrees now, we need 381 borehole meters, and then we stay beautifully within the limits. If you go to our inlet temperature, which is again a little bit lower, it's worse, so we need more borehole meters in order to make sure that every inch of pipe, let's say, stays above our limit. Here we need 434 total borehole length. For the outlet, again, it's less because this is the most optimistic temperature. Perhaps not so much suited for design, because typically you want to stay within certain limits, and you can specify this best at the average or the inlet temperature. But here you need 338 borehole meters. So this was what I wanted to say about the average inlet and outlet temperature. Perhaps it's all a little bit, or should I say it, vague. It's perhaps not something you use to differentiate between, but let's give it a go. It's really easy to use. It's also implemented in the reports as well. So it's also transparent to your end user what you used to simulate with. and I'm looking forward to seeing you in our next video. Take care. Bye.